Yo! So today we're finding all zeros. This is day 2 of our notes. And so we're going to try to figure out how to find all the zeros of these polynomials if we don't get that kind of hint we got last time where they gave me one of the zeros to help me break it down. So let's see, at the top of our notes here we got this first example, find all zeros of this polynomial. So first thing we scan for, are there any greatest, or is there any greatest common factor? And no, there's nothing we can take out of there from all terms. Next, maybe we could try factoring by grouping. But if I took out an x squared from these first two, that would leave me with 3x minus 5. And I don't think there's anything I could take out over here that would leave me with 3x minus 5. So factoring by grouping doesn't work. So at this point, we're kind of stuck. We don't really know what to do yet to find these zeros algebraically. We could kind of cheat this and graph and look for where it crosses the x-axis, but maybe we'll do that later. Okay, so we do have a method to find this algebraically, which is kind of a guess and check system. Okay, so here's our theorem that we're going to use today, called the rational root theorem. It says for a polynomial that has integer coefficients, we don't have fractions, that's in standard form, if it has any real rational roots, they have to be in the form plus or minus p over q, where p represents all possible factors of the constant, so it'll be like our constant at the end, and q in the bottom here represents all possible factors of the leading coefficient. So in this example, that leading coefficient, or the coefficient of the highest degree term, would be a 1. Okay, so if there's any real rational roots, they have to be in this form, plus or minus any possible factor of the constant over any possible factor of the leading coefficient. And so we're going to make a list of these possible rational roots. And it's going to be like a list that we can use to kind of guess and check. Okay, so let's try this. So first thing we need to identify is the constant. So this is p. Okay, so our constant here is 12. Don't worry about that it's negative 12, just 12 in general. Okay, so this is our p-value. And q is the leading coefficient, or all possible factors of our leading coefficient, okay, which in this case is 1. So let's list every possible factor of 12. Well, let's see, we got 1, 2, 3, 4, 6, and 12, right? 1 and 12, 2 and 6, 3 and 4, if you wanted to list them as factor pairs. But those are all the factors of 12. Okay, q happens to be 1, and the only factor of 1 is 1. So luckily that's going to make our list much smaller than it could have been. Okay, so remember that has to be in the form of either positive or negative, all possible p's over all possible q's. So we're going to write our list as plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1. You can see where this is going. Plus or minus 4 over 1, plus or minus 6 over 1, plus or minus 12 over 1. Now, if this had more factors, we'd also have to do 1 over that other factor, 2 over that other factor. It has to be every possibility. Okay, so this is our possible rational roots. And of course, we can simplify these to plus or minus 1, 2, 3, 4, 6, and 12. Okay, plus or minus any of these numbers. So there's actually 1, 2, 3, 4, 5, 6 times 2. There's 12 different possible real rational roots. So either positive 1 is, or negative 1, positive 2, positive 3, negative 3, etc. And if it does have any rational roots, they're in this list. So we can guess and check all of them. The downside is, of the 3 roots of this polynomial, none of them might be real or rational. Well, you have at least one real, I should say, because you can only have 2 imaginaries or no imaginaries. So there's at least one real, but it doesn't have to be rational. Okay, let's go to our next one here. Let's find all of our possible real rational roots of this. So again, we're going to start with our constant, which is p. and our leading coefficient is q. So all possible factors of 6 are 1, 2, 3, and 6. And all possible factors of 3 are 1 and 3. Okay, so our list is going to be plus or minus 1 over 1, which is 1, plus or minus 2 over 1, which is 2. Notice I'm just simplifying them as we go now. Plus or minus 3 over 1, which is 3, plus or minus 6 over 1, which is 6. Okay. Next, we're going to do everything over 3. So I also have plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 3 over 3, and plus or minus 6 over 3. But you might notice a couple of these, if we reduced our fraction, 3 over 3 is the same as 1. And since this is a guess and check list, there's no reason to guess and check the same factor twice. That'd be just a waste of our time. 6 over 3 is also 2, which is already in my list, so we can eliminate that. So all of our real rational roots are plus or minus 1, 2, 3, 6, 1/3, or 2/3. Remember, it could be the positive or negative case of any of those. All right, so that's our list. This time we've got 1, 2, 3, 4, 5, 6 times 2, because remember, it could be positive any of these or negative any of these. And we would have to guess and check and kind of plug them in and see if we got 0. Okay, so let's go to our next one here, where we're actually asked to find all zeros. And I think this is the same one that we started with. So the first thing I have to do is, I know factoring by grouping doesn't work. We checked that earlier. There's no common factor. So we're going to have to make this list and do exactly that, guess and check. And luckily, at least to check, we can use synthetic substitution. All right, so let's make our list. All right, here's P. All the factors of 8 are 1, 2, 4, and 8. And then Q over here is 3. So my factors of Q are 1 and 3. So my list is plus or minus 1 over 1, 2 over 1, 4 over 1, and 8 over 1. So it gives me all the whole numbers. But I can also have 1 over 3, 2 over 3, 4 over 3, or 8 over 3. I'm off the screen here, sorry guys. Or 8 over 3. So it could be any of these, positive or negative. That's a big list to check. Preferably, I would not like to check with the fractions. You can use synthetic and plug in fractions and do some fraction work, but let's hope we run into one somewhat early here. Okay, so we're going to start by testing positive 1. So we're going to write down our coefficients, 3, -5, -6, and 8. And normally we put those labels above to make sure we're not missing any terms. Remember, if we were, we'd write a 0 for that missing term. Okay, so we drop down our 3. 3 times 1 is 3. We add, we get -2. -2 times 1 is -2. We add, we get -8. -8 times 1 is -8. Whoa, wait a second. We did it! Smiley face. Our remainder is 0. We plug in 1, we got 0 back. 1 is a 0 of our function. Of the 3, remember this tells me we need to find 3. Of the 3 zeros we need to find, we just found one. One of them is 1. And remember we said last time, if 1 is a 0, so if 1 is a 0, that means x minus 1 is a factor. And if x minus 1 is a factor, we can divide it out to find our remaining polynomial. And actually, we already did that here, didn't we? Like, we'd put in positive 1 in the box. Those are our coefficients. This not only gave me the remainder of 0, but this is my other factor, the constant x to the first and x squared. So I have 3x squared minus 2x minus 8. That's one of my factors. And the other one is the x minus 1. We just actually divided out. So we found one of the zeros. It's 1. The other two are hiding in this quadratic. So we could either try to factor our quadratic and hope it's factorable, or we could keep going through our list. But let's just try to factor our quadratic. I think that's probably going to be a little easier. So to get to 3x squared, it's going to have to start with 3x and x. I'll write my x minus 1 over here just so I don't forget about it. Okay, I need two numbers that multiply to -8, and I need my middle term to be -2x. So let's see, my factors of 8 are 1 and 8, 2 and 4. Pretty limited list at least. To get this -2, let's see, I think I can do, well, one's got to be positive, one's got to be negative. And I think the bigger one needs to be negative to add up to -2. So we're going to do, let's do -2 here, because that would be 3x times 2, that's -6x. And then I can put the positive 4 here. Right, these two give me -6x, and these two give me positive 4x, which together makes -2x. I think we got our factors here. So our factors are 3x plus 4, x minus 2, and x minus 1. And if we set them all equal to 0, let's see, this one's going to be the easiest. We get positive 1. It's a terrible x. We get positive 1 from this factor. We get positive 2 from this factor. And if we subtract 4 over, that gives me -4, and then we'd have to divide by 3. So we get -4/3. There's all of my roots, or zeros. And if you notice, they're actually all over here in my list. All three happen to be real and rational, and they're all in my list somewhere. So if we had kept guessing and checking, we could have run into another one, but luckily once we get to a quadratic, we can either try to factor it or we can solve that quadratic in another way. Okay, for our next example, we're going to find all zeros of this guy. So again, first thing we always scan for, is there a greatest common factor? And here the answer is yes. These are all even numbers. So to make my life easier, let's take this 2 out first. And that leaves me with x cubed plus 2x squared minus 5x minus 6. Okay, so already we've made our life easier by taking this 2 out. We just need to finish factoring this smaller polynomial. So let's see. I don't think factoring by grouping is going to work here inside my parentheses. So I think we're going to have to do our guess and check list again. Okay, but this time we can use -6 as our p-value and this positive 1 as our q-value, which is nicer than using 12 and 2, which have more factors and would give us a bigger list. So we've actually narrowed the list down a lot by taking that 2 out. That's pretty good. So don't worry about the negative part of the 6. We're just going to list factors of 6 itself, which are 1, 2, 3, and 6. And q, our factors of 1, are just 1. So my possible rational roots are plus or minus p over q. 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, and 6 over 1, which is 6. So that gives us 8 possibilities. Okay? Luckily, that's actually a pretty small list. And the nice thing is we can check the polynomial inside. We don't have to worry about that too. So that actually gives me smaller numbers to run through my synthetic substitution too. So let's try positive 1. Okay, my coefficients are 1, 2, -5, -6. Apologize for my handwriting here. Not very good on this. All right, let's drop down the 1. 1 times 1 is 1. When I add, we get 3. 3 times 1 is 3. When I add, I get -2. And -2 times 1 is -2, and that is not 0. All right, 1 didn't work. What should we try next? Before you go to 2, let's try -1. Remember, it could be plus or minus. Let's try -1. Okay, again, my coefficients are 1, 2, -5, -6. Okay, we'll drop this down. 1 times -1 is -1. When I add, we get 1. 1 times -1 is -1. When I add, I get -6. -6 times -1 is positive 6. Whew. Man, we got lucky. We ran into 1 on the first try in the last problem and the second try in this one. We got a remainder of 0 or an output of 0. We have found a 0 of my function. So we just figured out -1 is a 0. Which means x plus 1 is a factor. So if we divide out x plus 1, which we actually just did here, here's my other factor. -6 is the constant. This one is x to the first, and this is x squared. So we have 1x squared plus 1x minus 6, and the factor we just divided out, which is technically x plus 1, from our 0 of -1. Well, let's hope this quadratic factors out. Are there factors of 6 that subtract to 1? 3 and 2. So it is factorable. That's nice. Let's see. So they need to multiply to -6. So they're opposite signs. And to add up to +1, I think we want +3 and -2. And we've got all of our factors. And if we're finding the zeros, we set everything equal to 0. We get x equals -3, +2, and -1. Okay, and there are 3 zeros from this polynomial. We found them all. They're all real and rational, and they're even all in my list. All right, well, that was pretty nice so far. Okay, our last problem today, and feel free to go back and, if you need to, go back and pause the video, play it back again a little bit slower, etc. We got one more. Let's do kind of a word problem here. It says, find the expression for the missing dimension if the volume is equal to this polynomial. So we have this rectangular prism, and it's given me an expression that represents the volume. So first of all, we need to know the formula for volume of a rectangular prism. And if you remember from geometry, most of you guys had geometry or geometry honors last year, we need to multiply kind of our length times our width times our height. So volume is length times width times height. You multiply the 3 dimensions together to find the volume. Okay, well, it told me an expression for the volume. It's this massive thing, x cubed plus 9x squared plus 20x plus 12. That's the volume. And it equals, let's call this the length, which is x plus 6, times the width. It doesn't really matter which one we call which here, so let's just call that the width, even though it looks, well, we'll call this the width, I guess. Our unknown, I don't know what to put there, question mark. And then times our height, x plus 2. Okay, so I need to find these 3 things multiplied together gives me this. Let's see, so there might be an easier way to do this. If we think about, what if I had some sort of rectangular prism? I'm not going to try to draw a whole one, but we'll pretend those are all nice straight lines there. Okay, so let's say we had a rectangular prism. What if I told you the volume was, let's do 30. Okay, 30 meters cubed. And I told you this was 5 meters, and this was 2 meters. How could we find our missing dimension? So we're going to use that kind of same idea here. So if I know the volume is 30, and that equals 2 times 5 times our missing length, that's a question mark, what could I do to find that? I could multiply 2 and 5 together to get 10, and it's 10 times our question mark, and then divide both sides by 10 to figure out my missing dimension is 3. So that's one option. I could multiply these 2 together and divide that quadratic. That would require long division, though, because I'd be dividing by the quadratic I get when we multiply those together. Or, if we come back here, we could first take 30 and divide it by one of the factors. So we could divide away the 2, which would give me a smaller answer, and then come back and divide by the 5. And then I could figure out my question mark is equal to 3. So we don't have to do it all at once. I could just divide my big polynomial by x plus 6, take my reduced answer, divide it by x plus 2, and that should leave me with my final answer. So I think we've got a kind of a game plan where I could use synthetic rather than long division, which I don't know about you guys, but I'd prefer to use synthetic. So, all right, let's try that. Let me clear up some room here. It's going to be a second. All right, here we go. So let's take this and let's first divide by, let's do x plus 6. We're going to divide both sides by our x plus 6. We're going to use synthetic for this because we can, and why not? It's faster than long division. We can get rid of the x plus 6 over here. So negative 6 goes in the box. My coefficients doesn't look like we're missing any, so I'm just going to write the digits down. 1, 9, 20, and 12, all positive. Okay, so we drop our 1 down. 1 times negative 6 is negative 6. Whoops, just drop the 1 down, sorry. 1 times negative 6 is negative 6. When I add, we get 3. 3 times negative 6 is negative 18. We add, we get 2. 2 times negative 6 is negative 12. And good, we got a remainder of 0. It should be a factor of our volume. So that makes sense. And that's my remainder, constant, x to the first, and x squared. So this is our smaller volume. Once we've divided away, we've got 1x squared plus 3x plus 2. Okay, so we've made it smaller by dividing by x plus 6, but this is still equal to my question mark times x plus 2. So to finish solving for my question mark, we could just divide both sides by x plus 2. Let's get rid of our x plus 2. So we can do synthetic division again. You could even just factor this quadratic. It's pretty factorable. But let's say we're using synthetic division. Maybe it's not a nice looking factorable quadratic that we could have just easily factored. Let's put negative 2 in the box over here. And let's do 1, 3, and 2. Drop down our 1. 1 times negative 2. That's an awful arrow. Hang on. All right, drop down our 1. 1 times negative 2 is negative 2. We add, we get 1. 1 times negative 2 is negative 2. And good, we get a remainder of 0, a constant of 1, and a linear term of x to the first. So we get x plus 1 is equal to question mark. That is our missing dimension, x plus 1. By the way, this quadratic that I said was factorable, its factors are x plus 2 and x plus 1.